All right, good morning. Okay, let's continue the lecture here. Okay, 2 more lectures to go. Some students asked about the final exam already, so I think I probably should post something this week. But anyway, I think I mentioned this maybe a few times already. So final exam is not cumulative. Basically, we cover materials that we started after the midterm. However, whatever we have covered after midterm pretty much requires everything that we had learned before the midterm. So partial derivative, lines, planes, right, cross product, dot product, parametric equation. So those things we're not going to specifically test anymore in the final exam, but they are part of the fundamentals that you need to know in order to solve the questions for the materials that you learn after the midterm. So that's the nature for the final exam. Okay. Final exam is a closed book, and you are allowed to bring in the formula sheet that I have posted on the Canvas. Okay. But that's the only one you are allowed to bring in. No calculator is necessary, okay, so there's no very complicated calculation or integrals. And the other thing is the formula sheet, please don't write anything on it. Okay, so you can print out double-sided or two-page, two-sided, that's fine, but just don't write anything on the formula sheet, okay, to be consistent with everybody. Okay, so that's my exam rule for the formula sheet. So all you need to do is bring in pencils, okay, erasers, and that's pretty much it, and your student cards, okay, student number cards. Alright, so let's continue on here. So we started on the concept of a surface integral. Okay. So surface integral formula is fairly straightforward. So basically, this is the surface integral formula. What it involves is a certain surface, and this F is a vector field dot the n hat dA. N hat represented the unit vector normal to the surface. Okay. So F here, we often can think of it as something representing certain quantity. So the surface integral, basically what it gives us is a general concept. We call that, give us so-called the net flux. Okay. And this flux basically represented by this F here, okay, through a surface. Okay. So that's actually what a surface integral gives us. Okay. We covered 3 different special cases, okay, in terms of how to evaluate the surface integral. We covered a special case when we have just a plane z equal to a, and this is essentially a plane parallel to the xy plane, and maybe there's a boundary associated with the plane. In that case, then how much of flux going through that plane? So the idea is to figure out what n hat is, right? And also what are the 2 variables that we use to evaluate this surface integral? Because the surface integral is not it's not a triple integral over a certain volume, because it's basically it's a double integral over a certain surface. So all you need is 2 variables to conduct that evaluation, the double integral. And 2 variables out of the 3 essentially in the 3D space. So we have covered 3 different coordinate systems. Then when you pick the 2 out of 3, then you have either 2 out of the Cartesian, or 2 out of the cylindrical, or 2 out of the spherical. And for this one here, the dA can be represented dx dy, so they're basically picking the x and y as the 2 variables in this case. And the limits for x and y can be determined by the shadow of this S in the xy plane. Okay. Now similarly, if the surface is a spherical surface, it's centered around the origin, okay, then we pick phi and theta, because a sphere and it has basically constant radius whenever you pick a point on the surface. So that's why the a at here is constant instead of a rho, right, for triple integral. And similarly for the n hat, that's a unit normal vector to the surface. It's 1 over a x, y, z. A is the radius of the sphere. For every surface, there are always two directions normal to the surface. So you can either have a positive or negative. Right? Positive typically refers for a closed surface, especially refers to a direction that is outward, okay, to the surface. Cylindrical, similarly, okay, so this is n hat is positive negative 1 over a x y 0, and then we can use a dz d theta, okay, as the two variables for the double integral, and then dA is a dz d theta. So this is what we find in the previous lecture here. Okay, yeah. It seems to be a lot of formula, but actually, if you can relate this with the triple integral formula, you find a lot of similarities at here. It's essentially a simplified version, yeah. And you will have this formula in your formula sheet. Okay, so that's the three cases we covered, and let's look at the number 4 case, which is the last case. Okay, the last case we're going to look at is a more of a general function. Specifically, we call it explicit surface z equal to f of x, y. And this is something that we have when we cover multivariable function. Here is a function of 2 variables, and the first thing I did is to basically graph this function 2 variables to give you a sense of what it looks like, right? Now this one I call it explicit surface because the function you can explicitly express for the z at here. So z equal to f of x, y. You have an explicit expression for the z. Some surface, they call it basically implicit. Actually, that would be actually case number 5, but that would be the optional. You can look at it in my lecture notes. Okay, so for some surface, you don't have the explicit expression for the z. Okay. If this is the surface, okay, then how do we evaluate a certain surface integral? Right, this s that here basically represented by this z. Okay. And how do we evaluate this surface integral? Okay. So for this one here, we're following similar process, but slightly, I'll show you slightly different things here. Okay. So previously, when we have a different coordinate system, different surface, what we do is we try to figure out the n hat, and we try to figure out the dA, and then we put them together into the original surface integral, and then we evaluate, right? Yeah. Now for this particular case, okay, we actually can present this n hat d at the same time. Okay, so for now I'm presenting at the same time, and then I'll give you a different formulas separately. Okay. So first of all, without a proof, this n hat dA, okay, at here, okay, this equal to positive, negative, okay, negative fx, negative y, and 1 dx dy. Okay. So your formula wise, okay, the n hat dA, okay, in this particular case number 4, okay, we're not separating n hat, we're not separating to give the dA. You can actually use the n hat dA, okay, as one single entity, okay, in single formula to use. So I write it without a proof because the proof itself actually takes a bit of a time. I do have the procedures of proof in the formula in the lecture notes. Okay. So I encourage you to look at it. Okay. It's actually not too complicated for the proof. Okay. So for the proof, okay, it's in the lecture notes. Okay, So let's back to the formula here, and then actually I'll give you a not so rigorous a demonstration of this where it's from. Okay? It's not a proof, but I'll give you a sort of a demonstration. Okay, now back to the surface at here. Okay? If this is a surface z equal to f of xy, so we're trying to integrate over the surface. And now you look at the formula right here with n hat dA. So bottom line, you're going to substitute this formula back into this surface integral. So essentially, your original surface integral will become f dot n hat dA, which is this whole chunk right here, positive, negative, fx, fy, and 1, and dx, dy. Right. So this formula will become this one in here. So positive, negative depends on the question, right? The question actually will give you hints whether you use a positive or whether you use a negative at here. Right? In general, if let's say if the question says upward flux, okay? If the question, can you calculate the upward flux, okay, through this surface S? Okay. Then you choose the positive sign right here. So I'll explain a little bit in terms of why upward you choose this positive. Okay. And of course, if you're required to calculate downward flux, and then you choose the negative sign over here. So that's the operation wise, how would that be? Okay, yeah. Another tricky part is this F at here, okay, is a vector field. Very probably it has 3 different components. This is a 3D and NP. Okay. And each one of the components could be very well a function of 3 variables, okay, x, y, z. Okay. Similarly for n and for p. So each one of the components of the vector field is a function of 3 variables. So now, if you can imagine, if I put this vector field f back into this surface integral, so from here to here, and also this part of the formula and here. So what you do have here is you will have a mixture of a function x, y, z over here, and this fx, fy, they're partial derivative of this function f, so they're purely function of x, y, right? Yeah. But the vector field f, you do have a function of x, y, z. So there's also a z over there. So you cannot have 3 things, x, y, z. Okay? Yes? Sorry, didn't hear that. Come. Yeah. Yes, it still applies. Yeah. So basically, in general, yeah, the surface can be anywhere, right? Maybe part of the above the xy plane, part of the below xy plane. Yeah, you're absolutely right. But in general, here, this basically applies to all the situations. Positive refer to upward flux. Okay, good. I'll explain a little bit why this positive is this upward here. So bottom line is, okay, you cannot have x, y, z showing up at the same time in this double integral or the surface integral here, because we are integrating with respect to x and y, right? So we have to get rid of that z variable. So how do I get rid of the z variable at here? What should I replace the z with? if I have a z in the vector function, okay, if I plot back to this formula, there should be a z there. But how can I get rid of the z? Just erase it. That's one way of doing it. Yeah. What would be a more mathematical way of doing it? How do I get rid of z? Where are we integrating? We're integrating over this surface S, right? So that's your constraint basically. And what is the surface S? So what do we replace the z with? We replace the z with the surface function. Okay? Yeah. So the z, so basically don't forget the z at here is whatever the surface is, f of xy. So basically z is replaced with f of xy. And that's a very common mistake sometimes when you do this kind of calculation. Okay. And one more thing, okay, regarding this surface integral. So once you choose the positive sign or negative sign accordingly, and once you replace the z with the actual function, actual surface f of xy, so the next thing what you need to do is basically figure out the x and y limits, right, in order to calculate this double integral here. So, and the next thing here is finding x and y limits. And finding x, y limits is basically the same procedure as you have conducted for a regular double integral. So over here you have your surface, okay, z equal to f of xy, and the x and y limits can be found through essentially a shadow, okay, of this surface in the xy plane. So this is the shadow at here. Okay. And your xy limits are exactly the same procedure as a double integral at here. Okay. So x and y limits are determined, okay, from the shadow of this function in xy plane. Okay, so that's the xy limits. So now you think about it, if xy limits is determined by a shadow in the xy plane, so essentially you're left with two different options. So you either use Cartesian coordinates to find the limits, or what's the other coordinates for a double integral? Polar, right? Okay. So you look at the shadow. What does the shadow look like? Is it a rectangle or is it a circular kind of shadow, right? And then you can find the limits based on the shape of the shadow. And sometimes you could also combine that, if this question is a little more challenging, even combine it with a change of variable, right? If the shadow is not in a very perfect location. Okay, so that's essentially the procedures, right, for finding this surface integral when the surface is a explicit surface z equal to fxy. Okay, so before I give you an example right here, so I do need to point out a few things actually. It's not a rigorous proof, but just to jog your mind relates to what we have learned here. So again, a few comments in here. So first of all, if in terms of computation-wise, whatever I see from now, okay, for the next maybe 5 minutes or 10 minutes, probably really doesn't matter to the computation. Okay, so you can literally up to here you can calculate, not a problem at all now. Okay, I do find some of the time my comments from here for the next 5 minutes sometimes confuse some students here. Okay, but anyway, so if I have a surface Okay, z equal to f(x,y). And now, let's forget about surface integral. Okay, if I have a surface and I want you to find out, can you find a normal vector, or more specifically, can you find a uninormal vector to that surface at a certain point? Let's start with the normal vector first. What would be a normal vector to the surface at a certain point? Grading vector, right? So okay, let's start with the normal vector to this surface at here, okay, and then easily get to a uninormal vector. As Andrew said, right, grading vector is a candidate to the surface, which is basically normal to the surface. We learned that in our grading vector concept. So when you have a surface z equal to f(x,y), right, you can always write the surface into z minus f(x,y) equal to 0. So this is a surface, right? And this surface is always part of a level surface of another function, which is a w at here. Right. So this w, if you let the w equal to the left side, okay, and w is a function 3 variables, and when you let the w equal to 0, then you get a level surface, which happen to be this surface at here. Right. Remember that, right? So w equal to this. Now if you calculate the del w at here, which of course basically partial w over partial x, partial w partial y, and partial w partial z. Okay, and if I do the computation, the partial derivative, there are two terms in the w, z minus this, z. Okay, is from our function of z x here, so partial w here, you're going to negative fx, negative y, and then 1 over here. Right. So this del w is the gradient vector to the surface, okay, z equal to fxy at a certain point x, y, z. And this guarantee that this del w is perpendicular to z equal to here, or maybe more precisely, is perpendicular to w equal to 0, okay, or z equal to f of x, y here. So the grading vector, okay, I think if you recall that I have tried to differentiate the grading vector del w and the grading vector just del f. There's a fundamental difference, right? Yeah, if you recall that the del f gives you a 2D vector. It's in the xy plane. Okay, that's not the perpendicular to the surface. That's actually perpendicular to the level curve, right, of that surface. Okay. So this del w basically is a perpendicular vector to the surface at here. And that's the answer. That will be the normal vector to the surface at a certain point. But if I want it as a uninormal vector, let's call it n hat, okay, then it's basically the del w over its length, and that gives us negative fx, negative fy, and then 1 over its magnitude. Okay, so that gives us a uninormal vector n hat to this surface at a certain point. Is that good? Yeah. So getting back to the formula, for this general surface integral at here. So if you look at this, this is surface integral for this x-plane surface. So remember, at the beginning I said I'm not presenting you specifically n hat dA. So for this part of formula, what you can simply try to remember is as an integral part as a combined n hat dA, which is this one here. Okay, yeah. So, but now what I did give it to you is what n hat is now. So this is your n hat. That makes sense, right? So you have your n hat dA, which is negative fx fy 1, okay, and then dx dy or dA. Okay. So this is your n hat dA. I want you to do a little bit comparison here. So this is n hat dA, and this is n hat. So if you compare these two, you actually will be able to immediately write it down what the dA is. So this is essentially a separate information now, right? For one for n hat, one for dA, and then you have n hat dA together. So if you look at these two, if this is n hat, if this is n hat dA, and dA is actually equal to and this piece times dx dy. And if you don't believe me, you can try it. If you try n hat times dA, and you get the n hat dA formula. Try to multiply this with the dA, and you get the formula represented at the beginning, n hat dA. Okay, because essentially this numerator cancel this, the denominator cancel this numerator here, right? Yeah. Okay. Yeah. Again, this is optional. Okay, so these two at here, this is essentially you can look at the lecture notes how dA is derived. I do have a specific procedure how this is derived here, but it is for some of you who are interested. Okay, so let's say even though this is optional, but some of you probably interested here. One of the question, very typical question is this. So let's say I have a surface over here. Can you calculate the area of the surface? So what will be the area of the surface right here? Now if this surface is in the xy plane, so that's basically a typical formula we did in the double integral, right? If I have a surface, let's say a circle or a patch of whatever shape, which is actually an xy plane, and the area of that surface or that little region, you use a double integral over the r, then you get basically the surface, right? Okay. But this is a surface in 3D, then we can have a very similar question. What will be the area for this surface at here? Technically what you do, basically this is the formula. So you integrate over this surface and you get the area, right? And this A here is a very small patch, okay? And then you can integrate, basically adding all the small patch up, and you get a total area. Okay. So now you see the beauty here is the formula for the dA, which is this one. So you can literally plug in this. You can literally plug in this dA formula, and then all you get now is a double integral that deals with two variables x and y. And xy, you can find the limits based on the shadow of the surface in the xy plane. Right. So this basically is the formula for calculating area of the surface. And I want you actually, for those of you who are really like to think about further, I want you to compare the formula with the arc length formula. Okay. And fundamentally there are a lot of similarities between these two formulas. So area, arc length. Okay. So try to look at it at your spare time. Okay, so that's the first comments here. Okay, again, as I mentioned, this comments has nothing to do with the computation of surface integral. You don't have to know this comment in order to carry out the computation of surface integral for explicit surface. It's simply just for interest, like what n hat is, what will be the dA, right? And then there will be extended knowledge in terms of calculating the area of the surface. And the other comments, okay, the other comments is this n hat equal to negative n hat dA equal to negative positive in terms of the interpretation, right? The interpretation of this upward and downward information right here. Right? So let me just quickly explain this one. And what do we mean by upward, or what do we mean by downward right here? So remember I mentioned if you are required to calculate upward flux, then you choose positive. And if you're required to calculate a downward flux, then you choose the negative at here. Okay, so let's look at the positive sign at here, right? So when it's positive, your n hat dA, right, is essentially equal to equal to this. And that's a vector, right? If you look at this one here, that's basically it's a vector. And then you have to use this vector to dot the previous vector function f hat. So this essentially is a vector here. Now if I try to graph this vector, okay, for this guy here, if I try to graph the vector, so think about what would be the general idea of this graph here. If you look at this vector, how many components does this vector have? 1, 2, 3, right? There are 3 components at here. If I choose a positive here, so forget about the first and the second one here, okay? That really depends on your fx, your fy, and also the actual xy location. So it could be positive, it could be negative, right? But my third component, which is 1, and that's always what? A positive quantity here. And the z and the 1 in here, this is your z component. Okay, this is your z component, right? Yeah. So if I want you to graph out, can you sketch this vector at here, okay, with the last component always 1. So if you think about it, if I have in a 3D space at here, I pick a point, okay, I'm going to draw a vector which is this, with the z component always 1, always positive. So what do you think the vector will pointing to? Will the vector be possibly pointing this way? Not at all, right? Because this 1 at here, because it's a positive number, it's always a positive number. So that vector will guaranteed to be pointing always somehow, either this way or this way, but it's always pointing upwards. So that will be your n, basically your n hat dA direction. Right? And whichever direction pointing to, that also depends on the negative x, negative fy value. But because the 1, right, you always have a positive up component. So there is a positive up component at here. And that essentially is why the reason, if you're required to calculate upward flux, right, then you use this positive sign in here, because this formula, what it does is, right, this formula here is you're projecting this f into the direction given by the n hat, and that's f dot n hat means, right? Yeah. F dot a unit vector is projecting the f into that direction. And if you want it upward, then you have to project it into the upward direction in hat. So that's the reason for choosing positive or negative. Okay? When you have why is it positive and negative in upward components in here. Alright, so that's a lot of comments at here. So let's take a look at a couple of examples. F equal to Z T hat. This is the vector field. Surface S is Z equal to x squared plus y squared, and Z is between 0 and 1. Okay, and then we want to calculate the surface integral over this surface. So how much flux? What's the net flux over this surface at here? Okay. First step, you got to be able to plot some of the very basic surfaces, and this is a paraboloid. Okay, it's a paraboloid and looks like that. And Z is between 0 and 1, so basically this paraboloid will be chopped off, okay, at the top when Z equal to 1. So this point here is Z equal to 1. Now you also have to sometimes be careful. For this particular S, it only refers to the paraboloid here. Okay, it doesn't include the top surface. As a matter of fact, sometimes it probably will specifically tell you the S has both the top surface and the side surface, and that actually requires piecewise integration. Okay, good. So let's look at this calculation in here. Okay. Now, before we look at the calculation, okay, let's see. In this case, I'm actually more specifically, I'll look for upward. Okay, upward flux. So before we do the calculation, I'm gonna just go ahead. Actually, this is not necessary, but I'm gonna go ahead to sketch this vector field out a little bit. This is F equal to Z T hat. If I'm going to sketch this vector field, so the vector has only Z component. If I pick origin and here, so this is 0, so nothing, right? If I pick any point in the xy plane, so basically there's no vector exists in the xy plane. But now once I move up a little bit, okay, then you will have a Z component. So basically you will have a little bit something once you lift up a little bit. And at the far away from your xy plane, okay, and the bigger magnitude of the vector field will be. Right, so that's the F vector field. Good. At the same time, I could also just roughly plot the n hat direction for this surface. So n hat is perpendicular to the surface. Okay. So that will be the n hat. You can draw a few bunch of perpendicular normal vector to the surface. Yes. Because I wanted upward flux at here, right? So, okay. So now I'll ask you a question. Before you even start to calculate, what do you think the value of this surface integral would be? Would it be a negative value, or would it be a positive, or maybe a 0, or maybe, I don't know, right? So what do you think is the value of this surface integral, or the flux, for this particular case? Which one would you think?
Positive.
Positive, right? because all the vector fields are pointing upwards at here. So you think, if you look at this, if you think about a flow of something, there's always something flowing through this paraboloid surface, right? Yeah. And also because the n hat, right, is also upward this direction. So when you do a dot product f dot n hat, you pick any point dot n hat, you will always got a projection in the upward direction, right, or in n hat direction. So that's why you can actually immediately conclude you're going to get a positive value out of this surface integral at here. So essentially you're making the computation a little bit alive, okay, instead of just a pure dry computation, right? You don't have to do this every time. But let's take a look at the actual computation here. What would that give it to us? Whether that's really going to be a positive number or not. Okay. So let's use all of the formulas that we have learned. The d n hat dA is equal to negative fx, negative fy, and 1, and dx dy. So this is n hat dA at here. Okay, remember this f at here, okay? That's basically your surface function f of xy. Okay, so now I can calculate the two partial derivative. Here's your function f of xy, so this is negative 2x, negative 2y, 1 dx dy. That's n hat dA. Then I'll bring it back to this formula at here, so the surface integral f. Okay. F is 0, 0, z, that's the vector function f, dot n hat dA, so dot negative 2x, negative 2y, 1, and dx dy. Carry out the dot product. 0, 0, so that cancel these two, you get a z times 1, so just a z over here now. So z dx dy. And this is exactly the kind of scenario I'm talking about here. You have a mixture of x, y, z. You cannot have a z at here because you have only x, y, two variables. You have to get rid of the z. So, as I mentioned, you replace the z with the function surface function. As you're integrating over the surface, so you have to replace that with the surface function. So here's x squared plus y squared and dx dy. And over this surface S. So finally, it's all about x, y now, and it's basically about all about finding x, y limits. X, y limits can be found through this shadow of this surface. And you drop the shadow into xy plane. In this case, we got a circle, so we can find the xy limits based on the circle. However, this is where basically you have to always think smart. You don't necessarily always use the Cartesian now because it's a double integral, and you can choose either coordinate system, and we can use polar. Right, because we have a shadow which is a circle right here. And what will be the circle equation then? The circle equation is what? X squared plus y squared equal to 1, because the top surface here is cut down by z equal to 1. So when you plug 1 over here, you get a top curve, x squared plus y squared equal 1. So use a polar. And xy here will become r cosine theta squared plus r sine theta squared. And dx dy becomes r dr d theta. And limits for r 0 to 1, 0 to 2 pi. The term inside the bracket is r squared. And you've got r cubed. So altogether you're going to get pi over 2. Okay, so that's the idea of a surface integral for explicit type of surface. So if you look at the procedures added here, really there's really nothing new except the first part. As long as you remember what this one is, or you can calculate this one here, and also replace the z with the function f of x, y, and the rest of the work is exactly the double integral, right, in a certain region in xy plane. Okay. Let's look at another example. Any questions so far? Good. Okay, so this one here will consider a different vector function now, and also different surface. Here's a different vector function. Surface S is this x plus y plus z equal to 1 in first quadrant. And integrate to get the total flux over that part of the surface. Okay. Again, let's roughly sketch this surface. X plus y plus z equal to 1, and that should remind you immediately that's a plane, right? That's a plane basically. Now, how do I plot the plane? There are some tricks in terms of how to plot the plane. So for this particular plane, if you set any one of the variable to be 0, okay? For example, if I set a z to be 0, then you got a x plus y equal to 1. Okay? So basically, that's the intersection of the plane with xy plane. So when you intersect this plane with xy plane, you're essentially intersecting with a z equal to 0. Right? And you got x plus y equals 1 here. And similarly, if you put a y equal to 0, then you get another line in here. You got basically x plus z equal to 1. Here's x plus y equal to 1. And here is y plus z equal to 1. So that's the intersection between this plane and the two sides of this coordinate plane here. And we're talking about here just the first quadrant, and that's actually exactly what we're looking for. So this triangle, okay, is the surface S. And we're looking for the net flux over this triangular part of the plane in the first quadrant. Okay. All right, so let's follow exactly the procedures that we have done according to the previous one here. Okay. First part, this is the surface S. Okay. The only difference between this question and the previous question is what? Previous question, you have explicitly be given z equal to a function of f of x, y, right? So you're given this. But this question, okay, the only trick maybe is you're not directly being given this z equal to whatever. Okay. So what you need to do, you really just have to write it out. What is this plane, or what is this surface in the format of f of x, y. So because you need that expression for the f so that you can calculate what n hat dA is. Let's still calculate upward flux here. Okay, still do the upward here. N hat dA. So now I have my function f now. So I'm going to do the partial derivative. Partial derivative f over x, you get a -1, and then there's another negative. So overall you get a 1, 1, 1. And this is a very common mistake. In the final exam, I've seen many times when students calculate partial derivative like this. They write down the right formula, but then they give a -1, -1, and then 1. Okay. So the problem is this typically is the first step. This is wrong, then the rest of the computation is all wrong, right? So you have got to be very careful in terms of this kind of small mistakes that could cost you sometimes dearly. Okay, so now I'm ready to calculate my surface integral. And f at here is x squared 0, 3y squared dot n hat dA 1, 1, 1 dx dy. Okay, so calculate the dot product. X squared plus 3y squared dx dy. So everything is x and y up to here, so which is fine. So we don't need to replace any z. It just happened that this vector field, right, doesn't have any z component. I mean, it doesn't have a z variables in it. Okay. Okay. So up to this stage, you have x, y. So the x and y can be determined based on the shadow of this surface, which is the right triangle over there. This is not doesn't have to use the polar. You can use just the typical Cartesian coordinates to calculate these integrals, right? So you have two choices. You can use dx dy. You can choose dy dx. Okay. Let's say I'm using dx dy. So the procedure is you draw an arrow lines in the positive z-axis direction. First contact x min, second contact x max. So that gives you 0 to 1 minus y. Okay. Because the bottom here is x plus y equal to 1. And then sweep the arrow lines, okay, from left to right, from the edges, which corresponds to the y limits. That's 0 to 1. Alright, so this is very straightforward integrals here. There's no trick at all. So you can do the calculation, and you'll get a 1/3 for this integral. Okay, so that's basically the 4 different cases for surface integral. Okay. If you look at the formula sheet, they give it to you. So you do have the 4 different cases over here, right? So what I noticed in the past is, okay, a lot of students able to write it down, but then they're not able to further carry out the computation, right? So that's always the danger. You know, you think you have the formula now, right? And then you're actually not able to carry out the computation. So practice, okay, it's not a very difficult situation, right? Okay. All right. So, but before we move on to a different topic at here, okay, just to re-emphasize again surface integral, another scenario is, now in this case we're just calculating surface integral over this just one piece, right, of the surface here. Okay, but in many other different cases, you may be asked, for example, this one. If I consider a closed surface which has how many sides? 1, 2, 3, 4. So if I have 4 different sides, give me this enclosed surface at here. Okay, and if I require to calculate what will be the, let's say, outward flux to this enclosed surface, okay, that's a very possible situation. Okay, so that's basically a different type of question. So what will be the outward flux? Okay, essentially out of a enclosed surface. If that's the case, then very often that if you have simply just a sphere, then there's just one surface, right? But often in time, that enclosed surface actually has different pieces, right? Like this case, it has, if this is enclosed, you have 1, 2, 3, 4 pieces at here. Then in this particular case, what you have to do now is basically your however the many pieces, okay, all you need to do is just to carry out, in this case I have 4. Okay, I'll carry out 4 different surface integrals. Each one of them, okay, I'm neglecting writing f dot n hat dA for each one. So each one of them you have to do separately, and you have to calculate using the current surface, okay, to do the computation. However, you also have to be very careful. Let's say, for example, right? If I call the bottom S1, okay, and then this plane is S2, and then the side here is S3, and that's the YZ plane is S4. It's a little bit messy here. Okay, so there are 4 sides at here. Okay, S1 is bottom, S4 is YZ, and S3 is XZ. So now, if I do the computation of this, so S1 is the bottom here, right? And we're required to calculate the outward flux. So the formula here, I only give you one case, that is a plane parallel to the XY. And then your n hat is either positive or negative k hat. So for the S1, your n hat, this is actually easy. Your n hat should be what? Negative k hat. Good. But what's my notation? By S4 and S3, okay, are XZ plane and YZ plane. They are not part of the formula here. You see that? They're not a part of the formula. However, you can easily make an extension. So if this is S3, S4, for S3, what will be the n hat? And for S4, what will be the n hat? For S3, outward, what will be the n hat at here? Negative g hat. Good. So negative g hat. And what about this for the S3 at here? Okay. For S1, it's dx dy because it's a plane parallel to xy plane. But for the S3, okay, which is an xz plane. So what are the 2 variables for the double integral now? Instead of dx dy, it will be what? For the S3 plane here. This dA, basically the dA at here. See, this dA is dx dy, right? So what will be the dA for the S3? That's right. Okay. Yeah. And similarly for S4, I believe it's going to be negative I hat. Okay, for the S4, and that's this plane here. Okay, so in the outward direction, that will be negative I hat. And then dA, okay, it's in the ZY plane, so dy dz. Okay. So that's easy extension, right? So try not to be too rigid, you know, say, oh, I don't have the formula. Well, it's the same idea basically. Okay? Yeah, if you have a surface integral require that kind of surface. Any questions so far? Okay. Yes. Yeah. Okay. So let me draw this one here. Okay. So this side is S3, right? Yeah. And then this side is our S4. Okay. Yeah. And bottom here is the S1. Okay. And the inclined ramp is the S2. So our direction basically meaning the n hat needs to point outward. So for S3, your n hat is this way. For S4, your n hat is this way. For S1, your n hat is this way. So you can see n hat for the S1 is downward, opposite of the z-axis, and S3 is the opposite of your y-axis. So that's why it's negative j hat, and this is why it is negative k hat for S4. Good? Good. Okay. Try to be a little flexible. Read the question carefully. Okay. And often in time, if you're required to do a flux out of an enclosed surface, so the first step we have to identify how many pieces surface is there to enclose this region. Okay. And you have to basically do a piecewise. Yeah. Yeah. S2 is this part of the surface. It's the cover. This is your S2. The S2 is a plane. It's the example we have just gone through here. That would be n hat dA for this piece. Yeah. So for the S2, actually I'm not separating n hat separately, right? Because this is S2 is a standalone explicit function. The case number 4. Okay, so case number 4 here. Is it case number 4? You don't have n hat formula. You don't have dA formula. But if you want to know the n hat formula, you have it in the lecture notes. Okay. Yeah. You only have n hat dA formula. All right. So let's continue here. And now we have basically only 2 theories to go now. 2 most important theories. So 3 different concepts: divergence theorem, and Stokes theorem. Okay, so 3 different things we need to cover it here. Okay. First, let's talk about the concept of a divergence first, okay. And then we'll look at the 2 important theorems. Okay, so the first concept is divergence of, more precisely, okay, divergence of a vector field, okay, at a point. Now this is a new concept. I'm going to write down the definition first, and then we'll look at what exactly is the physical meaning this divergence is giving us. Okay, so definition of this one here is very straightforward. Okay, it's written as divf So basically divergence of this vector field F, and is equal to its limit. First, we will calculate a flux So this top one here is the flux, and the bottom here over the volume, okay, small volume enclosed by this S at here, and then let the delta V go to 0. Okay, that's the definition for divergence. Okay. I'll explain this a little bit and see what exactly does it mean here. Okay. Okay, so if you look at the definition, right? Look at the numerator here, and this essentially is the flux calculation. But in this case, it's the calculation of flux over an enclosed surface S. So that's what this symbol means. Okay, so it's an enclosed surface S. Whenever you have an enclosed surface S, and that surface will definitely give you a small region enclosed by it, right? And that's delta V at here. So the volume, delta V, is the volume enclosed by the surface S. Okay, yeah. So basically, mathematically, that's what this means at here. Okay. Top one here. So top one here is the net flux, okay, through the S. And delta V at here is the volume enclosed by the S. So now you can see the idea of this integral basically is the net flux over a volume concept. Let's call it unit volume here. So you have a net flux through a volume here. So if I want you to come up with a different name for this divergence, what would you call it? Flux density, exactly. You see, right? And that's exactly the name, right? It's called basically flux density. Very much like the definition for what's the other one? The circulation density, right? Circulation density, if you recall that, it's the limits when you take a ratio between the circulation over a certain curve, and then divided by the area enclosed by the curve. Right. But circulation density definition is the curl dot the n hat, right? Give you the circulation density. So here, net flux over the unit volume, and you get this flux density here. Okay, so flux density, and that's denoted by divf at here. And if we carry out this integral, we can try to prove it. You can take a look at the lecture notes in terms of detailed proof. So we can prove that the divf at here, okay, turn out to be just a very simple expression. So it's called the del dot v, which equal to this one here. So F at here is a vector field MNP, okay, a general vector field, has 3 components M and P. And del at here, as you recall, that del is the basically the operator, and that's partial over partial x, and partial over partial y, and partial over partial z, right? That's the operator. And we have used this del operator so far until right now in a 3 different kind of situations, right? What's the first situation? We use a del and apply it directly in front of what? A scalar function. And we have applied the del crossing a vector function. And now we have a dot product with a function here. So that's basically the application of this del operator in 3 different situations. Greetings, curl, and now this is called divergence. Okay? Yeah. So what does divergence actually give us then, right? You know, if I calculate divergence like this, if you look at the results headed here, first of all, the other thing I need also to be very clear is, what's the end results of a del f? What does that give? Does that give a vector or scalar? Scalar. Oh, sorry. A vector. What about this one here? Vector. And now what about this one? Scalar. Okay, good. So you have to be clear what does that each one of the operations give us. So now let's come back to divergence. If divergence gave me a scalar quantity, I don't know what it is, maybe 2 or 3 or 4 or -2 or -3, right? That's what scalar means, or even 0. Okay. But what does a number mean, right? What's the interpretation of a number? Okay. So going back to this concept here, divergence gives you basically, it's a flux density. So if I get a positive number, meaning the flux density at that location is positive. If I get a negative, that means it's negative, right? If I get a 0, it's a 0. Okay? Yeah. But what does a number actually mean then? Anybody give it a try? So you have a flux, basically something flowing, right, through a surface. So now, if you imagine, if I have the surface S here, getting smaller, 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 that's what limit does, right? And now you're end up with, instead of a surface now, that surface end up with what? Just simply a dot, right? A point. But the idea of it's still flux out of this surface here, right? Or it's a flux now out of a dot. So if you get a positive number, so that means what? It's as if you have something flowing out of that point. If you have a negative point, it's as if you have something actually flowing into that point, right? So basically, the divergence at here, okay, it gives you a concept of a source or a sink. So you must have all played with the hoses. If you turn on the water always flowing out of it. So you consider that hose as a source, right? As a source. Now if you go to the courtyard of the UBC Okanagan here, and if it happened to be a good day, then you turn on the water, right, in the fountain. And if you look at the center of the hole, the fountain here, what happens? The water all flowing into that hole there, right? So that particular hole, you can consider it as a sink. And if you happen to calculate divergence at that particular hole location, you will get a negative number. Okay? Yeah. Yes?
To make delta V go to 0, don't we have to redefine the surface function?
You don't have to. At that stage, if it's so small, then it's basically just, you can consider even just a sphere, right? A spherical surface around certain points. And it keeps shrinking it, shrinking it.
So do we redefine the bounds then?
It's an enclosed surface. Actually, enclosed surface does not have any bounds. Yeah. Okay. So, and the other cases you could also consider is how do you tell whether your tire is leaking air or not? Okay. So what you could say is, well, let's calculate the pressure, right? If the pressure keeps dropping, then it's leaking air. But alternatively, mathematically, what we could do is we can calculate divergence. So if I have air keep pushing out of the tire, so basically you have a divergence in this case. What do you think the value is? The positive or negative? Positive, right? So if you end up with a positive divergence for the air inside the tire, then you can confidently saying, well, there's a leaking in the tire here. Okay, yeah. But if you keep pumping air into the tire, and you observe this divergence, and basically you observe a divergence turn out to be a negative value. So that means you keep pushing the air into the tire. So that means you don't have any leaking of the air here. Okay, yeah. So that's essentially what divergence means. Okay? It gives you a sense of essentially whether it's a sink or a source. Right? But there is a very, very special case is when you use a del dot a vector field. Okay? This is a vector field at here. It turned out to be 0 everywhere. It could be this. Okay? It could be a 0 everywhere here. So this is actually very common in fluid dynamics. This kind of a field is called solenoidal field. Okay? Basically, if you have a divergence equal to 0 everywhere in the field, then it's called a solenoid field. Okay? Now, what does actually a divergence equal to 0 means, right? If it equal to 0, what would that actually physically mean? So let's say I have a surface at here, okay? And it happened if I pick any point, okay, inside this surface at here, okay, you get basically 0 divergence. Okay? So if I have a vector field, okay, passing through this surface at here, if this is 0, basically means however many goes into the surface will actually come out of the surface, right? So that gives you this del dot V, okay, equal to 0. Yes. That's not different from the conservative field, actually. Yeah, it's a difference. So at the end of the lecture, I'm trying to, yes?
So do you think of it as like mass n equals to mass L?
Something like that, yeah. It's the transfer concept, yeah. It's transfer of something from here and then out of here, balanced out. Okay, so if I have a surface at here, and the actual flow more looks like this. So what do you think the del dot V would be? Positive or negative? Negative. So there's more into it, right? There's more into it, okay? Yeah. And the other thing, before we finish it here, there are two very important, actually, two important formula, very easy to approve. Okay. So we can show the following two identities. I will kind of explain this to you when I finish the divergence and Stokes theorem. There are two important identities that are here. The first one, del cross del F equal to 0. The second one is del dot del cross V also equal to 0, always equal to 0. Okay. So trying to piece the information together. First one, del dot scalar, not del dot, del scalar function F. What does that give us? Gradient. They give a gradient vector field, right? A gradient vector field, we actually prove that is always what type of field? Conservative field. And when you have a conservative field, what's the results of its cross product? It's always 0. That's one of the things that we use to check the conservativity, right? So this is the first one here. Second one here. So basically this one here says essentially it's a curl of gradient equal to 0. And the second one here is a divergence of curl equal to 0. And the second one here, I'll try to come back to the second one when we finish the Stokes and the divergence theorem. Okay? Yeah. Actually, there's a for the first one, you can also try to remember. Okay, I like this cartoon in here. Gradients can curl. You get it? Yeah? So if that's one thing out of this lecture, that's probably something you should remember for at least the next couple of years. Anyway, so we'll focus on the last two theories in the next lecture. Okay? Yeah. Any questions so far? Okay, got good.